Welcome to the new series, Think Like a Chemist. In this series, we're going to take the concepts you're learning in general chemistry and apply them to challenging real-world problems. Instead of simply memorizing equations, we're going to evaluate, analyze, and create solutions using the highest levels of Bloom's taxonomy. The goal isn't just to get the right answer, it's to think like a chemist. Before we touch our calculator, let's think like a chemist. What information are we given? What are we trying to determine? And what chemistry concept connects the two? The first challenge will be a density problem. A museum receives a corroded metallic artifact recovered from a 17th century shipwreck. The curator believes the object may be pure silver, but another historian argues that it is a brass replica added during a 20th century restoration. The artifact has an irregular shape and cannot be measured directly with a ruler. A chemist carefully dries the object and determines its mass to be 184.726 grams. The artifact is then fully submerged in a graduated cylinder containing 85.40 milliliters of water. After submersion, the water level rises to 103.18 milliliters. Possible metal densities are given. Corrosion may have altered the measured density by up to 3%. Determine the experimental density of the artifact, the percent uncertainty due to corrosion, the most likely identity of the metal, which metals can be eliminated and why, the percent error if the artifact were actually brass, and whether further testing is scientifically justified. First, we should highlight the important information we are going to use. We have a corroded metal artifact. The object may be pure silver. Another historian argues it is a brass replica. The artifact has an irregular shape. The mass is 184.726 grams. The graduated cylinder initially contains 85.40 milliliters of water, and after submersion, the water level rises to 103.18 milliliters. Knowing that the corroded metal artifact has an irregular shape will be important for determining its density. Since we cannot measure its dimensions with a ruler, we cannot calculate its volume using a geometric equation. Instead, we can use volume displacement. When an object is completely submerged in water, it pushes aside, or displaces, a volume of water equal to its own volume. That means the increase in the water level is exactly equal to the volume of the artifact. Before we can calculate density, we first need to determine the volume of the artifact. The initial water level is 85.40 milliliters, and the final water level is 103.18 milliliters. To determine the volume of the artifact, subtract the initial water level from the final water level. 103.18 milliliters minus 85.40 milliliters equals 17.78 milliliters. Now that we know the volume, we have everything we need to calculate the density. Density equals mass divided by volume. Substituting our values, density equals 184.726 grams divided by 17.78 milliliters. Calculating, we obtain an experimental density of 10.39 grams per milliliter. However, we also have to take into account that corrosion may have affected the measured density by up to 3%. To determine the uncertainty in our density measurement, we can rearrange the percent uncertainty equation. Percent uncertainty equals uncertainty divided by the measured value times 100. Rearranging the equation to solve for the uncertainty gives uncertainty equals the percent uncertainty divided by 100 multiplied by the measured value. Substituting our values, uncertainty equals 3 divided by 100 multiplied by 10.39 grams per milliliter. Calculating, we obtain an uncertainty of 0.31 grams per milliliter. Therefore, our density is 10.39 plus or minus 0.31 grams per milliliter. Taking the uncertainty into account, the density could reasonably fall anywhere between 10.08 grams per milliliter and 10.70 grams per milliliter. Now let's compare this range to the known densities of the possible metals to determine which metal is the best match. Aluminum has a density of 2.70 grams per milliliter, which is much lower than our acceptable range, so aluminum can be eliminated. Zinc has a density of 7.14 grams per milliliter, which is also much lower than our acceptable range, so zinc can be eliminated. Tin has a density of 7.31 grams per milliliter, which is also outside our acceptable range, so tin can be eliminated. Brass has a density of 8.55 grams per milliliter, which is well below our acceptable range, so brass can also be eliminated. Copper has a density of 8.96 grams per milliliter, which is also outside our acceptable range, so copper can be eliminated. Lead has a density of 11.34 grams per milliliter, which is higher than our acceptable range, so lead can also be eliminated. Silver has a density of 10.49 grams per milliliter, which falls within our acceptable range of 10.08 to 10.70 grams per milliliter. Based on the density measurements and the uncertainty caused by corrosion, silver is the most likely identity of the artifact. Now let's determine the percent error if the artifact were actually brass. Percent error equals the absolute value of the experimental value minus the accepted value divided by the accepted value times 100. Substituting our values, percent error equals the absolute value of 10.39 minus 8.55 divided by 8.55 times 100. Calculating, we obtain a percent error of 21.5%. Since the percent error is much larger than the possible 3% uncertainty caused by corrosion, the data strongly suggests that the artifact is not brass. Now let's answer the final question: is further testing scientifically justified? Although density strongly supports that the artifact is silver, density alone cannot prove that the object is made entirely of silver. For example, the artifact could be silver-plated, hollow, or made from more than one metal. A chemist would likely recommend additional testing. One common technique is X-ray fluorescence, or XRF, which can determine the elemental composition of the surface without damaging the artifact. Now for the final challenge. If the artifact were actually a silver-plated brass object, how would that change your density calculation and conclusion? What additional experiment would confirm this? Try this question out, research, and let me know what you think in the comments.